not on. How's this? Is this better? Can you hear me now? Have I been talking this whole time and you can't hear a thing? I think that probably was the case. So sorry about that. Hopefully this is better. We're just talking about how to solve this 3D system by relating it back to a 2D system that we're more familiar with. So we're setting equations equal to each other, trying to find the point in the middle where they cross. We do that by setting the equations equal. We do some algebra, and then we end up with a value for x. Then we take our value for x, plug it back into the equation, and we end up with a value for y. So at this point, all of these things are numbers. And these numbers we can compute down, and using these numbers we can compute down and get a value for y. I'm not going to do that because that's not particularly relevant for what we're trying to do in 3D. But if you're trying to solve a system of two equations in 2D, you now have all that you need to do that. What we want to do, though, is take this 3D situation and apply those same concepts. So can I copy and paste between pages? Yes, thank you very much. So the concept is the same. We still want to find where they cross, but we have to use a little bit more fancy tools just because we're dealing with more variables. We're going to use some vectors and some matrices to make our lives easier. While it sounds complicated now, the concept is the same. The implementation looks largely similar. We'll just have to be careful of a couple of things later down the road. So the first thing that we're going to do is, well, we have our slope, but it's in angle form. So what we need is we need to convert this coordinate for P1, so into an equation, and out of this angle set of coordinates into a rectangular coordinate space, something that we can deal with. So first let's write an equation for P1. We're going to say P1 is equal to this pointing vector, whatever this is, we'll call that V1 hat. So V1 hat times R1 plus T. That's not the best way to write it. It's fine. Now, before I start getting lazy with notation, I want to show you everything that I'm going to be doing here. When I do this little hat on top of the V, that's to tell you, A, this is a vector. So let's do a highlight. That vector. In fact, so is T, and so is P. Those are all vectors. And before you get scared off, all that means is these are numbers that have direction and magnitude, just like a positive or negative number. It's just in more dimensions. We can point it at things, which is lovely. Thing to take note of is this little hat and the difference between the hat and the arrow. The arrow, when I write it, not everybody does it this way. I do because it makes it better for me. But the arrow means, let's write a little more neatly, means vector of unknown length. Or arbitrary length. vector of arbitrary length. The hat means unit length vector. Length is 1. And that's significant because that means the length of this whole piece is R1. This whole piece is R1. And we can represent it this way by saying we have our length times our pointing vector, or our slope, plus this offset, this base point. Now, we're not particularly interested in where P1 is, or what V1 is, because we can measure that. We don't know R, and we don't know T. But we can find them, because we have two equations. So P2 equals V2 hat times R2 plus the same point T. V1 hat is equal to the conversion from spherical of a length 1, angle theta 1, phi 1 vector in rectangular. So this is spherical. And V1x, V2x, not V2, V1y, and V1z in Cartesian, which is just rectangular XYZ like we think of it. Same with V2. Length 1, theta 2, V2 in spherical. And the conversion back and forth between those is trivial and known. V2x, V2y, V2z. And we will get to that later today if we get to it. That's not super important for what we're doing at the moment. When we go to implement this in code, and I think I'll do that because I started to last week before I realized that I wasn't streaming to anyone. And partly because I think it's really cool to see the progression go from, okay, concept, I want to do this thing, here's the math to do it simply in 2D, here's the math to do it in 3D, here's the general case in 3D with more than just 2 beacons, and here's the code to do it. And now we can eventually take the code to do it, pair it with some real world hardware, and make the robot do it. And that's a project that I want to do, it just may be later down the road. And that is an X. So now what we're going to do is we're going to say, okay, I'm not interested in this whole business with P1 over here. I want T over here because I want to solve for T. So what we're going to do is we're going to rearrange a little bit. So we've got T equals, and I'm just going to subtract this piece here from that side. So we'll do P1 minus V1 hat times R1. And same thing with this second point, P2 minus V2 hat times R2. Which is lovely. Now we can set them equal. Over here, we've got P1 minus V1 times R1 equals P2 minus V2 hat times R2. Fantastic. So we want r by itself because we don't know r, but we do know the p's and the v's. P1 we're assuming because these are beacons with known locations, like a lighthouse or a GPS satellite. Those positions are known. V we know because we're measuring it using a camera or something of that variety. R is the only unknown here, R1 and R2. So we'll do P1 minus P2 equals V1 hat times R1 minus V2 hat times R2. Now, this business over here is a little bit funny. We have vectors and scalars multiplying each other, which is fine. And I'm actually going to move the r's to the other side of the vector just to make it a little clearer what I'm doing here. So this side doesn't change. P1 minus P2 equals R1 times V1 hat. Don't need a parenthesis there. V1 hat minus R2 times V2 hat. Now, we're going to combine some things into a matrix multiplication. So if we did this, R1, R2, row times column times row. Yeah, let's write this correctly. We'll do, and I'm going to do several notations here just to kind of pound the point home. We're going to do V1 hat here, and this is a matrix, negative V2 hat times R1, R2, and this is a vector. Let's take all that and move it over a little bit because I'm in space. So, mental note, this matrix, this vector. And if I was going to write out the vector or the matrix all the way, it would be V1x, V1y, V1z, negative V2x, negative V2y, negative V2z, times this R1, R2. Something outside's making noise. And when you do this multiplication all out, you end up with yes, V1x R1 minus V2x R2 V1y R1 minus V2x R2 V1z R1 minus V2z R2, which is what we see over here in this area. This is just our side note. So that you guys understand what I'm doing and why. So we're going to say R, let R equal this vector R1, R2, and we're going to let V bar, notice there's no arrow, that's because this is a matrix, not a vector, equals V1 hat, negative v2 hat. And I'm going to leave it to you guys to remember that this thing over here I did, this side note I did over here relates back to this, because I don't want to write it all out again. Although I guess I could just copy and paste. That's probably better. Duplicate. Like so. Now then, with those done, we'll rewrite this equation. Nothing's changed, we've just changed notation. We've renamed some things and put it into a mathematical form that will let us do this more easily. So we have P1 minus P2 equals R at V bar matrix times R vector. Okay? This is lovely because now this looks, minus the bars and arrows for vectors and things, this looks just like a regular old linear equation. Because, fun fact, it is. The only thing we got to be careful with is we can no longer divide by V. Because V, you can't, 1 divided by a matrix doesn't make sense. Doesn't make sense for V bar an element of for a matrix, which is all that's saying. This R, just as a side note, means real numbers. And this part means it's a matrix that's n by m. Rows by columns, yeah. So we can't divide by V bar. What we can do is multiply by the inverse matrix, so the multiplicative inverse, which we would write like this. And one more thing to note, since this is linear algebra and we're dealing with matrices, A times B, so A bug flying around. A times B does not equal B times A. There's no guarantee of it. There are some cases. Oh, excuse me. There are some cases where that does happen, but as a general rule in matrix multiplication, that's not the case. So, we have to multiply on the same side. So what we're going to do is we're going to say multiply this whole thing. I'm going to switch colors just to make it a little easier to see. Let's go blue. V bar inverse. Easy enough. So we'll say V bar inverse times P1 minus P2 vectors equals equals V bar inverse times V bar times R. Now, since this is the multiplicative inverse, this ends up going to 1 or the identity matrix, which is the equivalent of multiplying by 1 in the matrix world. So then we have, and I'm going to switch sides so that R is by itself on the left, R equal to V bar inverse times P1 minus P2 which is lovely. Except you don't have a guarantee of an inverse for all matrices. In fact, for matrices that are not square, so if there's more elements in, excuse me, there's a bug flying around. If there are more elements going left and right than there are going up and down, or vice versa, there's not the same number, it does not have a true inverse. However, you can have a pseudo inverse, which is the next best thing. And if you want to do some more research into that, you can. The method that I'm using for finding the inverse is called the Moore-Penrose inverse, or pseudo inverse. And that's written a little bit differently. Instead of a -1, it's going to be a V dagger. It looks like a T because I don't write fancy daggers. If you see it written that way on Wikipedia, that's what that means. And that is equal to, if I remember correctly, V transpose times V inverse. Now, a transpose times a non-transpose of the same matrix, so V transpose V, will always be square because you take the inner dimensions must be the same, which if you take the transpose they are, and the outer dimensions will have traded places, and so now you have outer dimension by outer dimension. Yes. Which is a square. So that inverse does exist. That can be unstable if you have a singular system. This goes back to our assumption earlier that we're not looking through one point to see the next one. So since we know that's not the case, this is more valid. In 3D, it gets to be a little bit funny because you can still have semi-singularities. If they're sufficiently close, since we're dealing with numerical systems rather than just symbolic, we have noise in our measurements and whatnot. This is good enough, though, for what we're doing. And this will be times V transpose. Yeah. So we're going to substitute and use the pseudo inverse, which will always give us a pseudo inverse regardless of our dimensionality. And in the case where we have a square matrix, it gives us the true solution. In the case that we don't have a square matrix, it gives us what's called the least square solution, which means it's the closest thing to what an actual solution would be. So we have R equals V dagger times P1 minus P2. Which is exactly what we're looking for. But suppose that I had more than just 2 points. Maybe I had 4 beacons, one in each of the top corners of a room, for example. That way, no matter which way I turn, I can always see at least 2 beacons. There's a way to do that, and it's not that hard. First thing we're going to do is we're going to rename this piece. We're going to call this B. Equals P1 minus P2. And to go up a level in dimensionality, which is what we're doing. It's not dimensionality, it's just order. To increase the number of equations that we're dealing with, we redefine some of these matrices and vectors. So for n beacons, we have R equal to R1 R2, R3, all the way through Rn. We have V bar equal to V1 hat, V2 hat, negative V2 hat. And this one actually gets funny because we don't move sideways, not only sideways. We actually have to turn this into a bigger matrix. So it's V1 hat vertically, V1 hat, V1 hat. Let's erase that. So this is 0, 0, 0, 0. This one is 0. This one is negative V3, 0, 0, 0, 0, 0, negative V4, 0, and no. This one goes like that. This one goes like that, like that, like that, like that. Trying to get my dots all going the correct directions for what I need them to be. And this is going to be 0, and this is going to be negative Vn hat. So that's how that matrix is defined. So we'll have regular V1s all the way up down the first column, and then on the diagonal for everything after that, it will be negative Vi, where I is 2 through the end. B changes just a little. It's still a vector, and it ends up being P1 minus P2, P1 minus P3. We've chosen P1 to be our reference, basically. P1 minus P4, all the way through P1 minus Pn. Which is also lovely. And is there anything else we need to define? I don't believe there is. So that's to find R's, which is great. Once we know R, that's lovely, but we're not really interested in what our ranges are. What we care about is where we, the robot, are, is where we are / where the robot is. English. And what we did before was we would substitute in our x. So, in 2D, we would do y equals m times r plus b, right? Now, I've combined, x1 and y1 and all of that into our full equation, but that's essentially what we were doing. We would substitute in x that we solved for somewhere else. Now, the same thing's going to go on here. In 3D, we have some t that we're trying to find is equal to, and let's scroll up and take a look. Where did I write that? P1 minus V1 times R. So it's going to be the same kind of thing. Equals P. Can I do that? Yeah, I can do that. Minus V times R. and this is pseudo math because I haven't vouched for all of this part yet. We've got to think it through. But P will just be a regular vector, and it'll be in the form P equals P1, P2, P3, all the way through Pn, like so. V is the same, just like we would expect it to be. No, it's not. Is it? No, it's not. So for this one, we want some V1 hat, V2 hat, V3 hat, through Vn hat times R. And R will be the same. So we'll call this V location. And let's correct this because that's not supposed to be a P, that's supposed to be a T. Dun, dun, dun. This is recording. Yes. Yes. Okay, good. Make sure this is all working correctly. I would hate to be trying to stream and then it just doesn't, but it looks like it's working fine, so we're good. Okay, so now we have everything we need to actually find all of our variables. Which means we can switch over to start writing some code, which I did last week, so I'll walk you through what I did. Where is it? Raycasting. This one. Switch to iChart. Yes. And we switched. Yes. So now we have code. And what this is going to let us do is start, making it so we can try this in the real world. So I've imported NumPy, which is the library that I'm using for vectors, matrices, all of my math stuff. I've created a class called Beacon, and what this does is it holds my information. So where is my anchor point and what color is it? That's partly for the display purposes, for when I go to plot things and make pretty pictures, and also partly for when I go to implement this on a robot. I want to say, okay, I have a beacon that's this color in this place, and then I'll measure it and stuff. And then down here I have my localizer. So I've written my transform from Cartesian to spherical right here. And this is that part that I said we'll get to later. This part doesn't matter so much, but here's the math if you need it. We take the vector normal to get the radius. Theta is an arctangent. And I'm using the 2-argument version that keeps track of the quadrant that we're in. And then phi is the arc cosine. and that converts our numbers and things. Spherical is the other way. It's just this set of equations, and then I multiply by the length. I've made this accept either a 2 or 3 long vector because I've done this code before, and it's really irritating to have to augment a a spherical vector that's just theta phi with the length of 1. So I just made it assume if I pass 1 in that's too long, automatically assume that it's 1, that the length is 1. So, how long have we been up? Almost an hour. We'll write a little more code. Nope. So now we can create, which one do we want to create? Let's pick this one will get created automatically when we do calculations and things. Let's create V. Oh. You can't see that. That's fine. Not that one. This one. This one. We're going to create V. So up here, my localizer accepts a list of beacons. This should actually be is instance beacons list. Yep. Okay. So these beacons contain, the anchor points and the colors, just like I said. And what we're going to do down here, oh good, I put as-el. I also want a class robot def init position. Position and position. And this should also be an is instance. And p.nd array. Okay. Anchor points. That's just for proper error checking, so that it makes sure that I'm putting everything in correctly. It'll throw errors and let me know usefully before it causes other problems down the line if I've done something wrong. So what we're going to do is we're going to take these beacons. Trying to think if this is the best way to do it. Probably I should have a robot and pass in the localizer and the beacon list. The robot will take measurements, so let's do it that way instead. Beacons. Self dot position So this is, I'm going to put an underscore in front of that because that's actual position. So actual position. And we're going to end up calculating what our theorized position is. So, nope, I have not. Okay. We want to create V. So let's def measure Azel. Yeah. So we're going to simulate getting the Azel measurements from our pointing vectors. Hey, if you guys got any math problems you want worked, go ahead and just pop it in the chat. I'll be happy to work it. Right now we're doing robotics localization stuff. So if we have a robot with a camera that sees two places that it knows, where is the robot? We've got some math done, so now we're turning our math into code. So right now we won't put in any noise parameters. We'll add that later. For now, we're going to say for beacon in self.beacons, we'll do, we're going to end up needing self.actual position minus, it's 2 minus from, so it's actually beacon minus beacon dot anchor minus the actual position, and this is going to be our pointing vector, and we will take these because these don't actually belong down here, I don't think. I know this one doesn't. So we'll put that up here. We'll do self Azel equals self dot cart to spherical, and we'll pass in pointing vector. Now this Azel is going to be 3 elements long because it's going to include our length. We don't care about length for this, so we're going to omit the first element and keep the rest. And so now we have Azels, and instead of setting it equal, we'll do element I equals that. We'll do I beacon in enumerate beacons, and Azels is going to equal np dot zeros, and it will be len self dot beacons long by 3 elements wide, because we have X, Y, Z. Seems good to me. Sure, now what we're going to do, so this loops through for all of the beacons and gets our Azel. So we will return Azels. And this may, yeah. think localizer is going to end up going away, which is fine. In fact, that's probably better. So now we'll do def create v. And the first thing we're going to do is take our as-else. So it will accept as-else. And if not is instance as-else is a numpy array, raise type error, because as-else must be a numpy array of shape question mark, because we don't care how long it is, but it has to have 3 elements wide. Nope, gotta be 2 elements wide, because we have 2 angles. We have our azimuth, which is up and down. No, azimuth is left and right, and our elevation, which is up and down. I should know this. I've done it, I don't even know how many times at this point. It's fine. So we're going to accept our as-else, make sure they're in the right format, and then v equals np dot zeros. We're just going to initialize the whole thing to 0 because it's easier that way. And now we have to convert from as-else back to Cartesian. Now, I know you're wondering, why did we just go from Cartesian to spherical if all we're going to do is go from spherical to Cartesian again? And the reason we're doing that is because I want to end up simulating with this. And what that means is I'll have to be able to inject noise the way noise will be added to the actual system. And the way that happens is in the angles, because we're measuring the angles via camera, which has pixels, and so we'll have pixels splitting up our azimuth and our elevation, whichever way it is. And so we'll have noise in the angles, not in the pointing vector. I hope that made some kind of sense. So now we'll copy this spherical to Cartesian thingy and pop that back up here. Minimize it because I don't care to look at them at the moment. And now we will do, we will set this up to be the correct size. So we have zeros, and the shape of it is going to be len. Let's take another look at our math. There we go. Math. So if we look at our number of elements, let's switch back to my board. We have it n tall, but remember that each of these is actually 3 elements tall. So it ends up being v1x, v1y, v1z. So we'll have it n times 3, and we have it n elements wide. And if I remember correctly, NumPy goes rows, columns. So when we switch back to this one, we'll do the length of self dot beacons times 3 by the length of self dot beacons And that is how big V is. So then V, the first column, is that right? Let's make sure that's right. Import numpy as np. So this is just the console where I'm going to test some stuff real quick to make sure that that ends up being the shape that I think it will be. So V equals, say we've got 3 sensors. So it's going to be 3 times 3 by 3. That is correct. Okay. And if I do V rows, all of the rows, okay, there's a nice, clever way to do this. It will be I don't remember. If you do 3, it skips every third element, or it skips 2 every third element. And I want it to do that for the first column. If I do that, that's just those though. Unless it'll let me do 1, 2, 3. Oh. No, not what I was going for. It's easy enough. There is a better way to do this, but I don't remember what it is off the top of my head. 3. And we'll go to 0 equals asels. Oh, gotta convert first. Almost messed that whole thing up. Pointing vector equals self dot spherical to Cartesian of asels. And if I remember right, I set this up to where I'll have to fix that in a minute. But we'll pass in asels, and it'll convert them to pointing vectors. And then pointing vectors, only the first pointing vector will make up that column. So it'll be that and x y, and z. So if I did that, if I do this, if I do that here, 1, we can do that, and then that, and then do V, and we can see it goes 1, 2, 3, 1, 2, 3, 1, 2, 3, which is exactly what we want. Next thing we're going to do is the rest of it. Smack. So we'll do v, and we're going to have to loop through now. So for I in I vec in enumerate pointing vec, which is our list of pointing vectors. Then we'll go I 3 times I, because that's our vertical offset, and all of these are in multiples of 3. So 3 times I through 3 times I plus 1. And we're going to take column I plus 1. Yes, is going to be equal to vector. But if we look back at our math, all of these have to be negative. So all of these need to be negative. And that part is this right here, which means all I got to do is -1 times that vector. And that should be v, created exactly the way we need it to, during v. So now if I come down here in my test code, I don't actually care about that. We're going to do robot, actual position, let's put it at the origin. md.array 0, 0, 0. Beacons equals beacon let's do I, 2i, I 3 times I plus 2 for I in range 3, 4. And we'll pass in beacons. And then we'll do print robot dot create v. Robot dot measure as else. And then we'll give it a run and see how many errors we get. Forgot about the color. Color equals, and for now we'll set it to 255 times, no, divided by 4 times I. That'll be fine. V must be length 2 or 3. Now I gotta fix that. So what's going on here is I've passed in the wrong shape of vector for the converter routines. So it's expecting the length to be 3, but I really, okay, so I should be using NumPy's stuff all the way through. v.shape 0, which is the length of it. But that means I want to take all of those and the first column, or the second column, first column, 0, not 0, all of that. That one should be good to go. So I've had to change it to be from being a single, wait a minute, did I do that right? I did not. Yeah. Had to change it from being a single vector converter to a list of vector converter. So then we'll come down here to do this one, and it'll be the same business. If shape, v.shape 1. Do the same thing up here. Yep. Is equal to 2. Insert into v into, hang on, np.insert object. Okay, and this is going to be np.zeros, and it's going to be v.shape 1. Let's make sure that that's correct. Go back to our console. V equals np dot ones, and we're going to do 2 by 7. Nope, it's going to be 7 by 2. Okay, so that's the shape I want for testing purposes. Index array argument object to insert dimensional or scalar. I see. Okay, so if I do this, and it did not do a thing. Did not do the thing that I wanted it to. Okay. So I just want it to do v equals v temp zeros, but it's going to be v.shape and this isn't going to be the best code probably, but it'll work. v.shape 1 plus 1 vt all of the rows, and the last of the columns will equal v. And that's what I want it to be. So v t equals np dot zeros, like that. It's actually going to be ones, like that, and vt all of the rows by the last of the columns equals v. Okay. And that's a hard copy rather than a soft copy. So I can delete vt and it doesn't get rid of v. That should almost fix it. that should fix it. Unless I've broken something else. V must be of length 3. In here. Cartesian to spherical. Spherical to Cartesian. Am I even calling that one? Yes, from here. Cartesian to spherical. We can... Oh, yes, okay. There we go. Print 1 by 3, which is what I expect. Print as dot shape 4 by 2. Why is it by 2? Because this one needs to be by equals. Oh wait, all of the columns. No, I don't understand. What's going on here? Okay, temp equals that equals temp. Print temp dot shape. Oh, I think. Does that work? Nope. Nope, it doesn't. 2. Okay. As else I that dot shape. Setting an array element with a sequence. I have done this before. Why are you complaining now? If you're watching and you have questions, feel free to pop them in the chat. Let's see. If I take that off. Can't broadcast from shape 3 into shape 2. Okay. That's good. Temp 1 on. Setting an array element with a sequence. Not sure what's going on. Divide by 0 encountered. Maybe we should check and see what's going into the as-else. Print pointing vector. Huh? Oh. No. Print temp. That's not correct. Cartesian. Axis equals 1. That's better. That's better. That's much, much, much better, I think. We'll do 0, 1. I was taking the normal along the wrong axis, so it was changing the shape of what I expected, or it was changing the shape from what I expected. From shape 0 into shape 2. Print temp. Yeah. We're gonna actually mp.stack these along r theta phi axis equals 1. I hope I can do that. Yeah. Okay. Broadcast from shape 3 into shape 2. Okay. Yep. 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 And then I can change this one to behave the way I expect it to. Yes. Okay. That's fine. We're now on to a different error. From shape 4 into shape 3. 1 times the vector. Alright, so print vector. Print vec. That is 4 elements long. I don't understand why. Okay. Oh, I might understand why. Print as-else. Those are the as-else, which is fine. That makes sense. And then what we're going to do is we're going to right here, because this is where it gets augmented. Print v.shape. It's 4 by 2, which makes sense. Okay, so then we're going to print VT. Yep, and that's fine as well. Also fine. Oh, okay. V equals np dot stack x, y, z. Let's see. Yeah. Axis equals 1, and this is going to have to move times that. This should work. Yeah, we're onto a different error, I think. Now we have an arrow here. Index 3 is out of bounds for axis 1 with size 3. Oh, it's because that's supposed to be a 2. Index 4 is out of bounds for axis 1 with size 4. Where are my printing things? Print vec.shape. This is doing what I think it's doing. Yes. Where's my other print statement happening? Oh, yep. Okay, don't care about that one anymore. Okay. Print vector. Okay, so we have 4 vectors that are the correct shape. And then it's iterating through them until it gets to the last one. Print pointing vector shape V shape. Okay, so it's 4 by 3, 12 by 4. Okay, so print vector, print I, print, yeah, that's fine. 0, 1, 2, 3. All right, so that means here it's trying to put it into 0 row, so from 0 to 3 in column 1. And here it's trying to put it in 9 to 12 in column 4. But it doesn't have a column 4 because the indices are off somehow. Because indices start at 0. is because this is not the correct shape. This needs to be that. +1. Yep. Now it should work. Boom. And that is V. Make it stop printing extra garbage. Boom. Create V. Why are you still... There we go. So that is how you create V. Now, we could go on, but I think this is a decent place to stop, and we'll pick up next week with Create B, unless I have some requests. So, if you've enjoyed this, be sure to subscribe, hit the like button. If you suspect that you may have math problems or just math questions in general, go ahead and join the Discord. I check it fairly regularly. If I can't solve your problem in the Discord, or if I think it's a good one for the stream, I'll pop it in our whiteboard chat, and I'll try and solve it on stream. So that's about it. Thanks for watching.